Hey, welcome to the first video in our structural analysis playlist, or course if you will. We're going to spend the first couple videos here just doing examples on drawing shear force diagrams and bending moment diagrams. Basically, I'm assuming that everyone, if you're watching this, you've probably seen these things before, but it's just good to get a bunch of practice. So we're going to spend about 10 videos doing various examples of different types of beams. Now, we're going to be doing this kind of the fast way. We're not going to be plotting shear and moment in terms of x. We're just going to be working off of a single free body diagram, and we're going to keep modifying that free body diagram to include new sections as we move across this beam. But with that said, let's go ahead and we basically want to solve for what the reactions are. If we call this side A and this side B, we basically want to figure out what the reaction A and B are, and when we do the sum of moments about A, we find that A is equal to 50 kilonewtons and B is equal to 30 kilonewtons. And that A there just comes from taking the sum of forces in the y direction. Okay, so now what we want to do is we want to draw on our shear force diagram and bending moment diagram, and then we're ready to start looking for our shear force diagram. So the way that we're going to do this is we're going to go from left to right. We can start off by having a virtual cut just to the right of this support, and when we look at that, we know that the support here is going to be 50 kilonewtons. There's going to be some internal shear here, and just to the right of this, an infinitesimally small distance away from it, this distributed load will be insignificant. So that means that this will have to be 50 kilonewtons pressing down. Now when we look at our positive sign convention up here, when we have a shear force pressing down to the right of a cut, that means that we have a positive value. So our shear force diagram is going to start off here at 50 kilonewtons, just right there. The one thing that we should also do is we should draw on some grid lines here that's going to be helpful to us, just because these are going to be points of interest. And actually I'll draw those on maybe just in gray so it's a little bit more discrete. That's good enough. And that's going to be another point of interest for us right there. Alright, so our shear force diagram up here is going to be starting at 50 kilonewtons. Alright, when we move across this distributed load, it's going to be increasing the shear or it's going to be increasing load pressing down on the member here. So what we would do is we just come onto our free body diagram here. We basically just want to include that. We'll take the whole thing, so 6 meters worth of 10 kilonewtons per meter is going to be a total of 60 kilonewtons pressing down by the time we just get to the left of this line. So just on the left of this line we have 50 kilonewtons pressing up, 60 kilonewtons pressing down, and now this internal shear force has to be 10 kilonewtons pressing upwards basically, or negative 10 in the downward direction. So that's going to put us down here at negative 10 kilonewtons. Alright, so we can connect those lines and then we can carry on. This section, the shear is not going to be changing because there's nothing going on in this area. So that'll be a straight line just like that, boom. And then when we get to just the right hand side of this marker, we're going to have to, on our free body diagram, we're going to have to include this 20 kilonewtons pressing down. So we'll just add that on. Now this free body diagram basically extends from A all the way just to the right of this section. So we have a total of 80 going down, 30 going up, and so that means we're going to have a shear force of 30 kilonewtons pressing up. That's opposite the sign convention, so that's going to be negative sense, so it'll take us down to negative 30, which will be somewhere about there. So this is negative 30 kilonewtons, and then we can finish off the free body diagram like that, boom, and that'll take us right to the end there. Alright, maybe let's draw on that last marker too. I think that's going to just make this kind of look a little bit nicer for us. Just like that, maybe a little bit less of a pen stroke there. Alright, close enough. One thing you want to do at this stage is you want to make sure that where we're ending with shear makes sense. So if we consider the free body diagram from the other side, if we section just to the left of that support, we're going to have 30 kilonewtons pressing up from that reaction force, and we'll have some shear force. Now that's going to have to be 30 kilonewtons pressing down in this region, and when we look at the left hand side of a cut, positive is in the upward direction, so that's going to be the negative, so it'll be negative 30 kilonewtons, and when we look at that, that's exactly what we're saying for our shear force right at the end there is negative 30 kilonewtons. Alright, so that's cool. That looks like we've done that properly so far. Now for the bending moment diagrams, if you remember from previous courses that we've worked on, where we have areas of the shear force diagram that are in the positive side of the axes, that's going to give us, basically we'll take the area of that, and that will be the change in magnitude of our bending moment diagram in the positive direction. Where we have areas on the negative side, that will be a change in magnitude, this area, that will push our bending moment diagram towards the negative side of the axis when we go from left to right. Now that does mean that we're going to have to figure out how far along this point is here. So we're going to draw this. Ooh, maybe let's do that a straight line. So this line here, this distance from here to here is going to be important to us. The easiest way to do this, I think, if it's not really evident by just looking at this, you can just do similar triangles. So in this case, we have, for this triangle, we have 50, let's call this distance x, basically, from there to there. Alright, that's going to be called x. So this triangle's rise over run basically is just going to be 50 over x is going to be equal to this other triangle, which goes from here like that. Alright, that one, its total rise is going to be 60 because it's 50 plus 10. And its run is 6 meters. So 6 meters. Alright, so when you do 6 times 50 divided by 60, we're going to find out that x is equal to 5 meters. Which means that this distance here is also going to be 1 meter. So that other distance, let's call it maybe x1, and let's call this guy x2. So we're going to get x2 is equal to 1 meters. Now, this one is pretty, you could have just eyeballed that, saying that this one's a little bit easier to see, but often it's not that easy, and just quickly doing this will be the most foolproof way of finding out this the x location of this. Alright, so we're going to use that information to find this area in here. So the area of this triangle, that's going to be 1/2 base times height, which is equal to 1/2. The base is 5, the height is 50, and 1/2 times 5 times 50 is going to be equal to 125. So that is we know that this is a beam that has to be, has a bending moment of 0 at the end, because it's not a rigid connection. These pins can't build up any internal bending moment like that. So the beam starts at 0 and ends at 0. And in this first section, from 0 to x equals 5, the increase in magnitude is going to be this area, which is 125. And these are in units of kilonewton meters, and up here these were units of kilonewtons. Cool. So where we also have, if you remember from the Mechanics of Materials playlist that we did, where we have a shear force diagram that is, or maybe that video actually showed up in statics, I can't remember. Anyways, where you have a shear force diagram, sections of the diagram where this line is not horizontal, where it's sloped, we're going to be getting a parabolic shape in our bending moment diagram. So it's going to look something like that. And where we get this crossing 0, you're typically getting a local maximum or minimum on the bending moment diagram. Okay, so here we have this triangular area down here on the negative side, so this will be negative 1/2 base height. The base is 1 meter and the height is 10. So this area will be equal to just 5. Now it's on the negative side, so the change in magnitude on the bending moment diagram will go towards the negative side. So it's going to bring us down 5 units, and that'll bring us down to 120 kilonewton meters. Alright, and again, this is, you can even draw this on, it sometimes helps. Because when these diagrams are really short like this, you can't really, if you're doing this on a test, your teacher might have a hard time determining whether or not you've drawn a parabola or a straight line, so we'll just say parabolic in this section and parabolic in this section. Cool. Now these next two sections have horizontal lines in the shear force diagram, so that's going to just give us linear changes in magnitude here, so basically just sloped lines. When we look at this area in here, it's just a rectangle, so it's base times height. This is going to be, its base is 3 meters, times its height is 10, so this will be a change in magnitude in 30 across this distance, and it's on the negative side, so it's pushing us, that change in magnitude is pushing us towards the negative direction. So 120 minus 30 is going to bring us down to 90, just like that, and then you will just connect this with a straight line, boom, like that. you might want to label on here. Linear, just again, good practice so your teacher knows that you know what you're talking about. Alright, when we look at this next section in here, this is also a rectangle, so the base is also 3 meters, and the magnitude, or the height, is 30 kilonewtons. So 3 times 30, that's going to be 3 times 30, that will be 90. So that's going to be a change in magnitude from here to here towards the negative direction of 90, and look at that, it's going to bring us, oh that's ugly, that's going to bring us down right to 0 as we expected, so we can label on those zeros as well. So there we go, we got the shear force diagram with all of the basically the critical points on there, and we also have the bending moment diagram, the general shape. We know where it's parabolic and we know where it's linear. And then we also get these key points every time it's basically switching into a new region there. The one other thing that we can do if you want, or if it's being asked of you, is you can draw the deflected shape. So we had a simply supported beam up here, and its deflected shape, basically if you're drawing your bending moment diagram, it's you can kind of eyeball it. It will more or less be sort of like the mirror image of this. So our deflection is basically just going to be more like that. It's just going to sag down. It's probably sagging a little more to the left, but sometimes your teacher will just ask you to draw the general shape, and this would be basically sufficient and enough to say, yeah, I get that when we load a beam with stuff pressing down on the top like this, it's basically going to sag down a little bit. Sometimes when we have overhanging beams though, it's like a little bit less intuitive, but as long as you'll be able to use the bending moment diagram and some information that we get in more complicated problems to basically just show that you kind of understand the way that these beams are bending